good morning, or good afternoon, I should say. I hope you're all well. So for any of you who saw the keynote this morning, there's no virtual reality in this session, so it's just plain old traditional core storage. My name is Cormac Hogan.
I'm Cody Hosterman.
And so we're going to talk to you about basically the core storage changes that have been happening in vSphere, but in particular we're going to focus on vSphere 6.5, the most recent release, I guess. So we do have to put up the usual disclaimer. We're not going to be talking about anything really forward-looking here, I guess. But we have to put it up anyway. So by way of introduction, I work in our storage and availability business unit at VMware, part of the office of the CTO there, do lots of things around storage, as you can imagine. Cody?
Yeah, my name is Cody Hosterman. I'm the technical director at Pure Storage for VMware Solutions. Been at Pure for a couple years. Prior to that, I was in the EMC and the VMAX group. As you can see, I shaved because facial hair does not work well with me. So that is gone now, thankfully, but it's an old picture.
And the whiskey is gone.
The whiskey's, yeah, the whiskey's completely gone. It's empty.
Cool. So this is what we kind of had a bit of a brainstorming about what we would talk to you about. We're going to talk about some of the new limits that were introduced in 6.5. Cody will kick that off. I'm going to talk to you about VMFS 6 and all the improvements that we have made to that most recent version of VMFS. Then Cody will come back in. He'll talk about our array integration primitives, commonly known as AAI, which I can never say properly. So in particular, there's two parts of that. The ATS, Atomic Test and Set part. That's the replacement for the SCSI reservation mechanism. And then the UNMAP, good old UNMAP. We've had quite a long and checkered history with UNMAP, so Cody will fill you in on what we've done there. I'll come back in then and I'll talk about what's essentially I/O filters. I don't know if many of you have heard of I/O filters, but this is a way of plugging into the I/O path of a virtual machine. So with vSphere 6.5, we released two I/O filters, one for encryption and one for storage I/O control. I'll talk to you about those, but there's also the ability for partners to plug in here as well, and I'll talk a little bit about that. I'll then talk a little bit about NFS, some new enhancements for version 4.1, a little bit about iSCSI, and Cody will finish off then with talking about what we've done in the NVMe space, and then we should have time for some Q&A. Sounds good? Okay.
Sounds like a plan. Alrighty, so let's get into it here. So first thing is device limits. Right? So traditionally, ESX had a limit around 256 devices per host and 1,024 logical paths. Right? Generally, the limit I saw people run into was the pathing limit first. But certainly I saw customers run into both. Right? And so these numbers have been doubled in 6.5, right? So if you have a lot of devices, if you have a lot of paths, or those devices have a lot of paths, right? This limit is a lot larger in the latest release. This should help a good amount of customers. Important thing to note though is that if you have more than 256 devices per target, like on a single array, ESX won't see that because the way it does its LUN ID counting and so forth and the mechanism that it uses. But overall, if you have like 512 devices, they are now supported. The limit for virtual volumes is very different. Right? We're not going to really go into a lot about virtual volumes today, but there's a deep dive, I think, tomorrow morning or something around it. But this limit does not apply for virtual volumes. You can have a lot more. You see a big number right there, virtual volumes, than you have traditional SCSI devices. Another thing that's been changed was sector size support. Right? So if you have an array that supports 4K sector size, this is now supported with VMFS 6. Now you'll see it's kind of reported inside of the CLI and the GUI or whatnot as 512E, 512 emulated. This is now supported. Right? Mainly this has been introduced for scale perspective on certain arrays. They wanted a larger sector size so they could have larger scale, and this is particularly important with VMFS because now it's 64 terabyte limit for a while now, so this helps some storage arrays that need this larger sector size. If you look at the CLI, you can see some changes in 6.5 when reporting these, and you'll see, it's this 4K sector size, this is 512 emulated, right? This is supported with VMFS 6. I would say, in the end, the main difference you're probably going to see from like a user experience is that if you go to do boot from SAN, where it auto installs VMFS, if it's 512E, it's going to use VMFS 6. If it's the traditional 512 sector format, right, 512 native, it'll default to VMFS 5, right? I see that question come up. There was a subreddit about this a couple weeks back on the same thing, right? So that's probably the one thing you'll note from a difference perspective in managing and using VMFS. And I believe that behavior is going to change at some point. But as I said, we won't talk about futures.
Yeah, I suppose the one thing to point out is that we're looking at 4K native as well, right? Yeah, but it's not there yet.
All right, so one other kind of small thing that got missed a little bit in kind of the blog announcements and things was the change with disk.schedule number request outstanding, which is essentially a hypervisor level queue depth limit. Right? It says how many outstanding IOs or how many in-flight IOs you can have against a certain device per host. Right? And this is kind of VMware's limit on that, right? Above and beyond the HBA device queue depth limit. Traditionally, this was limited to 256, meaning you could have 256 outstanding IOs against device from a single host, and after that, it's going to start waiting inside of the kernel. Right? This was also limited, right, with the HBA queue depth limit. So the actual queue depth limit for a device was the minimum of DS&RO, which is now really called the number of outstanding IOs per world, and the HBA queue depth limit, right? So if your HBA queue depth limit was 32, your actual queue depth limit, regardless how DS&RO was set, is going to be 32. So in 6.5, VMware changed this. The maximum you can set DS&RO to is whatever the HBA queue depth limit is, which makes sense, right? So therefore, it could be limited to 12 if that's what your HBA is set to, or it could be limited to 2,000 if that's what your HBA queue depth limit is set to, right? So this opens up from a performance density standpoint in VMFS inside of a host if you really want to push a lot of concurrency, a lot of IOPS and throughput to that device, right? So this is a change in 6.5.
Okay, cool. Thanks, Scott.
You're welcome.
Yeah, so VMFS 6 then, the latest release of VMFS, came with vSphere 6.5. And so I'm just going to talk about some of the major changes that we've made to VMFS 6 compared to the previous versions of VMFS. So this is the first one. This is not to be confused with the actual on-disk file block size that still remains the same. But what we have the ability to do now is, depending on the type of file that we're going to create on VMFS, be it a thin disk or a thick disk, we can pre-allocate the space using these new file block formats. So we have a small file block format. It's still the 1 meg in size. So when you're creating a thin VMDK, that's the file block format that will back that. But the major enhancement is when it comes to creating thick VMDKs. We now have this large file block size of 512 megs. So what that means is that very quickly we can allocate space on the VMFS for your thick files. Now you might say to yourself, well, I only use thin, so this isn't relevant to me. But where it's also relevant is when you power on your VM, the creation of the swap space for that VM, swap is always thick. So what you'll find is that that swap space is now created very much quicker as well. So the power on time for your VMs will increase with VMFS 6. Okay. Yeah, so that's the first enhancement. So this is the second one. I'm sure most of you know that the VMFS is made up of a bunch of system resource files. The thing with these system resource files in previous versions of VMFS is that they were static. So they were built depending on the size of your VMFS, and they were pre-allocated in advance. What we have in VMFS 6 now is the ability to grow these system resource files. So we'll start off with a certain size of system resource, and then depending on the more files that we create, or perhaps extending that VMFS 6 volume, we can build additional resource files or scale out those resource files. Now I think, Cody, you said you had an issue with some of your customers where the pointer block resource used to run out. So there could still be space on the volume, yep. But then the resource file for the pointers meant that we couldn't extend.
Yeah, I've seen this increasingly recently where, I mean, because of all flash arrays, right, there's a lot more concurrency they can offer for volumes, and so people were leveraging VMFS to larger sizes. But unfortunately, they would exhaust pointer blocks, and when you go to add a new VM or grow within virtual disk, it's like, oh, I'm out of space. But I was like, no, I still have 32 terabytes left on this, but they would exhaust those pointer blocks. And so this is a big improvement for using larger VMFSs and actually being able to use the larger VMFS.
Indeed, good stuff. So theoretically now, we were limited to a certain number of files that we could create on VMFS 5 and earlier. Theoretically, we could grow to millions of files being on a VMFS 6 volume. So what I did is just by way of an example, I built a VMFS 500 gig VMFS 5, and we'll just have a look at this. This is a way of just dumping out the metadata associated with that VMFS 5. I'm not sure if you know that command or not, but it's quite useful just to see. Just to prove it's a VMFS 5, you can see I highlighted the version number there. It's still the 1 meg file block. This is the on-disk format, and a few other things to look at there. The number of subblocks, it's set in stone essentially, and so on. So I do the exact same thing now on VMFS, and I dump out the metadata once more. I can now see that this is the VMFS 6 volume, and what I find, it's still the 1 meg on-disk format, but I do now have these large file blocks that I can see. So this is going back to this pre-allocation of space. What I did there is I just built a few very large VMDKs on this VMFS 6 volume, and you can see that it used these large file blocks that I mentioned previously. Something else that's interesting, the subblocks now is half of what we had on the VMFS 5. On the VMFS 5 it was 32,000. Here we only have 16,000. But the thing is, as I consume them, I can dynamically allocate additional ones. Something else that might be interesting here, I don't have any pointer blocks. So for those of you who look at this on a regular basis, you might be curious about why we have no pointer blocks. What we've done in VMFS 6 is we use subblocks for pointer blocks. So that's why this pointer block structure has gone away on VMFS 6 as well. So the next thing then is a new system resource file. So we use a journaling, so VMFS is a journaling file system, so because it's clustered as well and so many hosts can update it continuously, if there's a situation where there's a failure or whatever the case may be, we use the journal to maybe replay or roll back and just validate that what we attempted to write to disk actually was written to disk. However, journals just used standard file blocks, and we came across a situation where this was problematic. It was problematic for a reason where you might have filled the file system. So let's say your file system, your VMFS 5 is completely full. So the one thing you'd want to do is you'd want to go ahead and you'd want to maybe delete some files off that file system and free up some space. Well, unfortunately, the journaling mechanism required getting a file block in order to do that delete of a file, so track that delete of a file. And so we had this kind of chicken and egg situation where we couldn't delete files because we had to get a journal entry. The journal entry required a file block. There was no space left on the file system. And so, we had to get you to jump through hoops. There was a specific KB article that talked about how you could turn off journaling and all that stuff. So all that means that we now introduced a separate system resource for journaling. Okay, so it's no longer consuming file blocks, it's got its own resource now. So it's got a new system resource file. If you're looking at those system files in the header of a VMFS volume, you'll see a new one on VMFS 6 called JBC, and that's the system resource for the journal. And just to show that I'm not telling you lies, captured the output there. The top one is your VMFS 6. You can see there's no journal resource file, but the top one is VMFS 5, there's no journal. The bottom one here shows you the new journal resource. Cool. So this one is quite interesting. This is VM-based block affinity. So it takes a little bit to describe as well. So we have a number of hosts. All these hosts are sharing a VMFS, and now we're going to build VMs from a host on that VMFS. So it's fine. So what we do is we will allocate a bunch of resources to a particular host in order to build a VM, VMDK and so on, and that's absolutely fine. So we have a host and it's got resources on the VMFS volume. It owns that resources, there's no contention there. It owns these VMs, so it's absolutely fine. There's no problem with contention arising. However, if that VM is then vMotioned to a new host, now you have two hosts sharing the same set of resources on the VMFS. And so now, if both of these hosts get a request to grow the VMDK on these two VMs, they'll both go and look in that resource group or cluster, and they'll both attempt to grow the VMDK. So they want to get new resources from the same resource group to grow those VMDKs. And that's where we've seen conflicts arise in the past. This is especially true if you have lots of hosts sharing a VMFS volume, if you have lots of VMs on that VMFS volume. And so this was down to the sort of host allocation method we had for blocks. So what we've done with VMFS is we've moved towards a VM-based block allocation mechanism. So now what happens is that we instantiate a new VM or create files for that VM. We look for these resource groups that no one else is using. And so every new VM will be given its own brand new resource group. So now it doesn't really matter whether the VM is vMotioned between lots of different hosts. The resource group is specific to that virtual machine, and there shouldn't be any contention. Now that's the first thing that we try and do. But obviously, as you have more and more VMs, as you consume more and more space, there might be a situation where there's no free resource groups left available. So what we do in that case is we look at all of the resource groups, we look at how many VMs are using those resource groups, and we'll pick the resource group that has the least number of VMs for this new VM. And so we're trying to reduce the contention there as well. But this move towards VM-based block affinity as opposed to host-based block affinity should reduce considerably the contention that we would have seen in the past where multiple hosts are trying to access the same set of resources. Okay? And I think this is, actually we have a demo on this as well. I think this is going to be quite an eye-opener for you. I suppose one of the things that has been a bit of an Achilles heel in the past is to do with LUN discovery, device discovery, file system discovery. And so those operations on a per host basis were always sequential. We couldn't do parallel discovery operations prior to the vSphere 6.5 release. So what we now have in vSphere 6.5 is the ability for a host to do parallel queries on, are there LUNs out there, are there volumes out there, and so on. And so this is quite a major enhancement, and I think when you see the demo shortly, you'll see how much this has improved things. This is especially true for any of you who might be doing DR and failover and need to do maybe a resignature operation on a whole bunch of volumes, especially for something like Site Recovery Manager. If any of you are using Site Recovery Manager, this will speed up the failover time considerably. And I think it's last but not least, this is something that was very close to my heart. For the longest time, if you had a VMDK that was 2 terabytes in size or greater, we couldn't hot extend it, we couldn't grow it online. So we were forcing you to power off the VM, grow it when it's cold, a cold extend for want of a better description, and then power on the VM again afterwards. So with this release of vSphere 6.5, you can now hot extend VMDKs that are greater than 2 terabytes in size. So it's a nice addition, something that I've been hoping we would get around to for a long time. So I do have to finish on a bit of a bum note, I'm afraid. There is no in-place upgrade to go from VMFS 3 or 5 up to VMFS 6. There simply has been too many changes to the underlying file system that it wasn't really possible to do something that allowed you to do that in place. Too many changes to the file system structure and so on. So if you're considering going to vSphere 6.5 and also going to VMFS 6, which I would strongly recommend, you do have to plan for a migration mechanism. And we got a fly up here, sorry.
We're sweating up here.
Yes.
It doesn't smell good.
So you do have to plan for, maybe evacuating one of your VMFS 3s or VMFS 5s or whatever, reformatting as a VMFS 6, and then using techniques like storage vMotion and so on to migrate the data back. So just bear that in mind. There is no in-place upgrade to go from a previous version of VMFS to VMFS 6. So that cool demo, I think, is going to come up in just a moment. I'm going to take over there, but
Yep, sure.
there you go.
Alrighty, so I'm going to do a live demo here, so let me start the video. Okay, so what I'm demonstrating here is resignaturing a bunch of volumes at once. So essentially what I'm doing is I have a snapshot of a VMFS, and I'm bringing up 8 copies of it. This is something that we see happen quite a bit, and I'm using PowerCLI, of course, to do this, where people bring up lots of volumes for dev test scenarios, right, or Site Recovery Manager or whatnot, and this could take a long time. All right, so I kicked off 8 resignature operations here at once, and it doesn't really matter if it's 8 ESX hosts or 1. I'm using 1 here, but really the same issue applies, right? And this can take a very long time. And this is one of the reasons we did a video, because this would be very boring to watch for the next 5-6 minutes. And so we will skip ahead here and then move to the end of this resignaturing process. But the parallelization around this really has changed, and it was kind of funny. I mean, when I was recording this video demo, I was telling them, like, hey, I've only got it to be about like 20 times faster. This is horrible. It definitely was 40 times the last time I did it. Right? So the resignaturing process here took about 5.5 minutes to do all these at once. And I've seen it take 45, 50 minutes sometimes in larger environments. Right? I think my environment was too clean. Right? So what I'm going to do here is I'm going to kick off the same process, right, with ESX 6.5. Now, the thing to note about this is you do not need VMFS 6 to benefit from this. This is an ESX storage layer enhancement, right? How it manages and looks at and locks VMFS. Right? So VMFS 5, VMFS 6 doesn't really matter as long as you're on 6.5. A lot of these enhancements we're talking about is around the same way. The thin hot extend, same thing. If you're on ESX 6.5, just works. Doesn't matter what VMFS version are. But there are certain things that we're talking about that are specific to VMFS 6, and of course we're going to call this out. So the resignatory process here takes I think about 20, 25 seconds or so instead of the original about 5.5 minutes, right? And so this is a particularly big improvement, right, especially at scale. When you have disaster recovery plans that requires resignaturing VMFS volumes, right, and your RPO is important, right, RTO rather, this is particularly important, right, of reducing the amount of time to get that storage back up, resignature, and you see the rescan's already kicked off. Right? And so said about 20, 30 times faster, right? And I can see that, I've seen that improvement go up and up in other environments.
But I think it's, we had to make these type of improvements because, as Cody highlighted in the limits section at the very beginning, we've gone from 256 to 512 devices. So I think this is a big improvement for sure. Yep.
So VAI, right? VMware continues to enhance. I'm not saying we anymore this time. It's okay. VMware. I'm pure. VMware continues to enhance VAI, right? Add new features, make it better, make it faster, right? VAI in general, right, is a bunch of offloads, right? Having the array do things that VMware knows the array can do better than itself, right? Xcopy, write same, atomic test and set, right? A variety of different features. So one of the major enhancements here was with atomic test and set. Sometimes referred to as hardware-assisted locking or compare and swap. It goes by many names. And one of these is around heart beating. Right, so traditionally, heart beating is well, let's go back. Heart beating is around making sure a host that has access to a data store is still alive. Right? If it has VMs running on this data store, this allows the other host to know, oh yeah, this host still has locks, it's still running, it's still working, I don't need to take over these locks, or I shouldn't take over these locks. Right? And so ESX servers each have a host heartbeat region on that VMFS to say, yeah, I'm alive, yeah, I'm alive, yeah, I'm alive. Right? And of course, there are processes around acquiring these locks, clearing them, reacquiring them, and so forth. Up until ESX 5.5, we've update 2, I think, this was done. The liveliness of it, actually setting the timestamp and so forth, was done using SCSI reservations, right, which is a performance problem. Right? And so using atomic test and set was mainly for extending VMs and also some of these other heartbeat operations, right? Actually acquiring it, clearing it, and so forth. And the heartbeats themselves are essentially timestamps, right? When it was last set, when it was checked, and so forth. But introducing ATS support for heartbeat liveness, right, did introduce some issues. And so this has been fixed in 6.5 with how they handle what they call a miscompare, essentially where ESX will send its heartbeat check down, and for some reason that heartbeat check fails with a miscompare. Right? And what would happen with that miscompare essentially is that, oh, the timestamps are off for some reason, something's wrong, tear down the storage stack, right? You could lose access to your devices and so forth. And this was an ugly problem, right? Losing access to your storage. I mean, access to your storage is the whole reason for storage, right? So that's just not a good thing to have, right? And so VMware has fixed this. There's a variety of reasons this happened. There were some issues on the VMware side with having too short of timeouts. There were some issues on the array. Sometimes the array was overloaded and they would return a miscompare. Sometimes they just returned a miscompare for certain reasons. But VMware didn't do some more due diligence to make sure that it was actually an accurate miscompare. So this has been changed and fixed in 6.5, where it'll actually look to see, is this actually a miscompare? Right? It'll look at its test and set image and see the timestamps. Is it actually a miscompare? If it's not, it'll go back, it won't tear down the storage stack, and then it'll retry in a bit. Right? And vast majority of miscompares are false. Right? So that issue where it would tear down the storage stack for really just because of a mistake is not going to happen. Right? So now, if it then comes back again and it is a miscompare, then okay, the same behavior is going to apply. But a lot of those best practices around arrays saying, hey, turn off ATS heart beating, no longer should apply for 6.5. Of course, talk to your storage vendor, but this problem has been fixed from a VMware side, internally inside of ESX, how they handle it, and also how to handle issues from arrays.
It's fair to say there was a lot of finger pointing going on with this initially.
It's a lot of root cause analysis on that one.
Array vendor, they're pointing at us, so hopefully this puts an end to it.
Blame it on the network.
Exactly.
All right, so another major update to VAI in 6.5 is, of course, UNMAP. So the concept around UNMAP is with block storage, right? And this is not just a VMware thing. This is any OS or any hypervisor, right? If you delete a file, if you move a file off of a data store, the underlying array doesn't know it, right? It's going to continue to preserve that data, right? And this can happen in a variety of places. It can happen on a VMFS, right? You delete a VM, you move a VM, the array doesn't know it. Inside of a VMDK, if you delete a file from NTFS or XFS or something like that, the VMDK doesn't change and the VMFS doesn't know it, and neither does the array, right? So the array is storing what they refer to as dead space. And a mechanism that was introduced about 15 years ago or whatever in the SCSI spec to do this was called UNMAP, right? And just other forms, trim for kind of direct SATA and so forth. And this allows you to tell the underlying array, hey, these logical block addresses, no longer need them, right? Go and reclaim them, do whatever it is that you do with unused space. So one of the major enhancements here is Automated UNMAP is back, right? There's been a bit of a journey with UNMAP. This was released in its first form in 5.0. Now it is back in 6.5 in a much better form. Okay. So in 6.5, UNMAP is an asynchronous process. Right? So when you delete a VM, when you move a VM, the ESX 6.5 hosts accessing that VMFS 6 volume, remember this is specific to VMFS 6, have a background UNMAP crawler that will issue UNMAP to those blocks over the course of time to reclaim that space. This is a default configuration. If you format it with VMFS 6, it will be turned on. It will be turned on to a priority of low. There are only two priorities, off and low. There's some documentation out there that say medium and high. That is, I don't know what's the word, misleading, wrong. It's not activated in the code yet. So either none or low, right? And they'll reclaim space. Now, it does require 1 meg UNMAP granularity on the array. So there is an HCL around this. So certainly check to see, make sure your vendor is supported with automatic UNMAP. So from a kind of, understanding of how this works, it will not happen in 5 minutes. It will not happen in 30 seconds. Space reclamation can take 12 to 24 hours, right? It is a background asynchronous process, right? This is what VMware did to make sure that, hey, if arrays aren't super friendly with a lot of synchronous UNMAP, a lot of I/O around that, it'll still behave nicely and it won't overwhelm the queue depths or the array itself from deallocation. You can stop a host from participating. There's a kind of a hidden CLI setting, enable VMFS 6 UNMAP, that if you don't want a host to participate in this for some reason, you can disable that host from participating. The setting, though, to enable it for VMFS in general is a per data store setting. If a host does not have an active world on that VMFS, meaning a VM that's running, it will not participate in automatic UNMAP. Only hosts that have VMs that are currently running on that host, on that data store, will monitor that VMFS for space reclamation. So if you don't see space being reclaimed after a day, it's probably because you may not have any hosts that actually have VMs that are running on it, right? Then maybe you could either run your manual VMFS unmap traditionally like you did before, or kick off a VM, have it running, I don't know, whatever, right? So that's one thing to note about this. So that's VMFS unmap. What about in-guest unmap? This has also been quite dramatically enhanced inside of 6.5. So how in-guest unmap works is ESX now allows the guest OS, Windows, Linux, whatever, if it supports unmap, to be able to issue unmap to its own virtual disks, right? NTFS, XFS, ext4, whatever. Right? After it deletes a file and moves it, it can issue unmap to it. Then ESX, the virtual SCSI stack, will intercept that. It shrinks the virtual disk, right, in accordance to the amount of space that was reclaimed. And then ESX will issue unmap down to the VMFS itself to reclaim it physically on the array. So this allows end-to-end guest unmap. Now, the virtual disk must be thin, right? It does not work with thick virtual disks today. So initially, in 6.0, this feature was introduced. It was only supported with Windows 2012 R2 and later. This was due to the fact that ESX at the time only supported SCSI 2. Linux, for instance, requires SCSI 5 support for unmap, which the virtual SCSI stack of ESX did not support. So it's like, hey, I can't do it. So the use case was somewhat limited to Windows. In 6.5, one of the major changes inside of it from a virtual SCSI stack perspective is that they now support up to SCSI 6, SBC 4, in other words. If you look at your virtual disk like inquiry information, you'll see it's virtual disk 2.0, right? And there's a whole new set of versions for SCSI support that you can actually see when you inquire on these virtual disks. And so this added support for Linux in guest unmap. So it does require the unmaps from the guest to be aligned. Now with Windows did not behave particularly well with this. It issued a lot of misaligned unmaps, even though VMware did everything it could to literally tell the SCSI stack that, hey, give me 1 meg unmaps. If the unmap was misaligned, it would just not work, it would fail, right? And so this made in-guest unmap with Windows somewhat flaky in 6.0. Now, in 6.5 patch 1, they have changed how they handle misaligned unmaps. So if the guest for some reason refuses to send aligned unmaps, ESX will, all right, give me the part that's actually aligned, I'll take it in, and the part that's not aligned, I'll just zero it out. All right, so the part that's aligned, it'll shrink the VMDK, and the other parts, it'll just zero out. So if you have arrays that do zero removal on the fly, like most AFAs, or you have arrays that can do zero space reclamation, this still will allow you to get all that space back. It just might take an extra step for that zeroed stuff. Now there were, oops, go back a little bit. There were some issues around this performance issue that was fixed in 6.5 update 1. So definitely if you're moving to 6.5, make sure you're at update 1 because there was some, when you had misaligned unmaps, there were some Windows issues around performance. Just out of curiosity, who is at 6.5 right now or in the next 6 months looking at moving to 6.5? Okay, cool, about half, that's great. All right, so let's do a quick demo of in-guest unmap. So what I'm running here is I have a Linux VM running on ESX 6.5. And what I'm going to do is I'm going to put some files on it. You'll see the virtual disk grow and then shrink. So my virtual disk right now is about 400 megs or so. Right, that's just kind of the formatting from ext4. And I'm going to throw just a bunch of OVAs onto it, just some files I had sitting on my laptop that I want to throw into this Linux VM to make it grow. Right, so I'm going to use the power of video to move forward. And we look at my VMDK and it's now much larger, a little more than 4 gigs. Right, so I added about 4 gigs of space to this virtual disk. And when you look on my array, the capacity for this, you see that data reduction makes it a little bit smaller, but there is some physical allocation now that I put those files on it. Now I'm done with those files for whatever reason, the database or whatever it happens to be, and I want to go and actually delete it. Right, so let's take a look at my actual file system first in my VM. We'll see the space that's actually used currently. We'll just df it here. And we'll see, yeah, I'm using about 4 gigs, right, of space. So I'll go ahead and I'm going to delete these files. I'm just doing it through here. I should have just done it in the SSH session, whatever. Now that it's gone, we'll run it again. And now it's down to basically 0, just whatever the reserved space of that file system. But my VMDK is still holding that. So in Linux, there are 2 options for space reclamation. You can run fstrim, which will manually issue unmap to dirty blocks on that file system, which is what I ran. And if you do it with a -v, it'll actually tell you how many blocks it ran to. Right? And this video will be posted online, so if you want to watch it again. When I run fstrim, it shrinks that virtual disk down back to the original 400 megs. The other option for ingest unmap is automatic for Linux. If you mount the file system with the discard option, it'll automatically issue essentially trim right to that file system to reclaim the space. If you don't have that mounted with the discard option, you can use fstrim. You can see the space has also been reclaimed on the array because ESX sent the unmaps itself. Right? So this works particularly well. So for Linux support, you need 6.5.
Cool. Good job. Thank you. Okay, so the next part of the demonstration is kind of talking about policy-based management, but more in the context of I/O filters. Now, I know a lot of you raised your hands for 6.5, already using 6.5. Are any of you using the new I/O filter mechanisms that we've released with 6.5, such as VM encryption or the next version of storage I/O control? Okay. All right. So just a little bit about I/O filters. Our SPBM, to be precise, we now use policy-based management extensively for the vSAN product and also for virtual volumes. But you could also use them for VMFS. This is where they initially originated. And using VASA, which is the storage awareness APIs, we can have storage arrays surface up certain capabilities, and you can then build policies around those capabilities. And the I/O filter mechanism, or VIO for short, VAIO, that's no different. That's also policy-based. And so how you consume these new I/O filters is through policies as well. So policies are quite straightforward. They're just a set of rules. I want a setting to be this. So when I provision a VM with a particular rule, it's going to check what storage is available, and that storage that matches the policy is where I'm going to locate my VM. So it's just, it's pretty straightforward stuff. And obviously, depending on whether it's vSAN or vVols or I/O filters, there's going to be different rules and rule sets for each. But you could also combine them together. So if you wanted an I/O filter with a particular type of storage, you could build a policy that contains those, or a rule set within a policy that contains those different rules. So for those of you who have gone through policies before, you might have noticed this screen as you're building your particular policy. There's some interest. Usually, I've just normally just clicked through this because I don't read that stuff too much. But there's some interesting information in here. So for instance, we have this thing called common rules, and these are for host-based data services. Now, when we talk about I/O filters, we're talking about host-based data services. So the VM encryption feature, the storage I/O control feature that we have, and also the I/O filters from partners. So we have partners who have cache acceleration I/O filters, and we have partners who have replication plugins as well. So all of these I/O filters, they're plugging into the virtual machine I/O path and providing a particular service. Okay? But this is where you'd select the host-based services. So this is where VIO or the I/O filters would come in. And then we have the kind of array-based services down here as well. And this is where you would consume policies for vSAN, vVols, and VMFS. So in this particular case, I'll talk a little bit about the two that are shipped with vSphere 6.5. So these are two data services that are available on vSphere 6.5 right out of the box. The first is VM encryption. We plug the I/O filter into the I/O path of the VM, and we encrypt the data in flight. And the second one is storage I/O control. I'm sure many of you are aware of what storage I/O control is. It's been around for the longest time now, but it's essentially a mechanism of putting guardrails around a noisy neighbor, a VM that's misbehaving, maybe generating too many IOPS, introducing high latency. What we can do with storage I/O control is we can put parameters around that particular VM to stop it impacting other VMs on the same data store. Okay? So now in vSphere 6.5, storage I/O control is policy driven as well. Okay? So let's have a look at those. This is again just continuing on in that in this wizard for setting up policies. We go into the common rules section, and now you can see the encryption and storage I/O control I/O filters available for you in there. And it's then pretty straightforward. Those of you who have used storage I/O control, you'll know about limits, shares, reservations. It's pretty much now we're going to build a policy around limits, shares, and reservations. But the cool thing is rather than going around to every single virtual machine and editing these parameters, we can now just build a single policy and apply that policy to multiple VMs at the same time. So this is where things become much easier using a policy-based approach. So as I said, you can customize it as well, so you can see the limits, reservations, and share values in there, depending on what you want to do. So encryption then, as I said, encryption is another I/O filter. It's available to you in 6.5. The one thing you do need though is a key management server. That's not something that VMware provides, so you will have to reach out to one of our certified partners, get their key management server, plug that into your vCenter, and then we can consume it for VM encryption. As I said, plug into the I/O path, so it's not only data at rest encryption that this gives you, but it also encrypts the data in flight from the VM. And again, of course, it's policy driven as well. So just to show you that very quickly, there's pretty much very little that you can edit within a rule for VM encryption. The only thing you can do is that if you have multiple I/O filters, so for instance, you have storage I/O control, you have now VM encryption, and maybe you're using some of the third-party ones like cache acceleration or replication, you can actually decide where in the virtual machine I/O path each filter is applied. So that's pretty much the only thing you can modify here. So encryption is essentially you turn it on or you turn it off.
And a good use case that I've seen around, at least the IOPS limits and so forth inside of vSphere, I've seen some customers deploy in 6.5 in particular, is around VDI. Right? Hey, I sized this VDI environment to 25 IOPS desktop. I want it to be at that. Right? And so using this as a policy is a great way of doing that at scale. Right? Array-based QoS is great, but like from a VMFest perspective, it follows the data store, not necessarily the VM. So there's a nice benefit around that. Cool. And of course, virtual volumes changes that, right? It kind of ties those things together. But at the very least, it's been a pretty successful use case from some customers I've worked with on it.
Excellent. Thanks. So just by way of a demo, I'm just very quickly going to run through that just to show you this live. So again, this is just looking at the storage providers. You do need VASA here, of course, and all of the ESXi hosts do have VASA now to provide you with the information required for VM encryption or for storage I/O control. So we're just going to build a policy very quickly. It's going to be host-based data service that we're going to consume, and so that's why we're using common rules, and in this case, I'm just going to set up a storage I/O control policy. So you can see there's the usual low, high, and normal settings that for those of you familiar with storage I/O control, you'll know about this. So it just has the IOPS limits and shares preset there. As I said, you can combine this with storage as well. So your policy could be a host-based data service that ends up on a particular data store. But in this case, I'm not going to choose a particular data store because I want to be able to use this on pretty much anything. And so that's my policy created. And now instead of going, like I said, hand editing those storage I/O control settings on each VM, at provisioning time of this virtual machine, I will be able to select the policy as I'm doing the provisioning task. And so you can see here, I'm just going to select a particular policy. All data stores are pretty much compatible, so I can select a particular one to put this policy on, and then just complete the creation of the VM. And so even though we're showing it here at the provisioning stage, the fact that you have the policy, you could apply that policy to already existing VMs as well. Actually, you can apply it to multiple VMs at the same time. So it's really by way of showing you of going from the approach where we had to maybe hand edit all the different virtual machines to set up storage I/O control. With a policy now, we can apply that to multiple VMs in one fell swoop. Okay. So the next thing I wanted to talk to you about is, not show you the demo again. Let's see.
Double click usually.
There we go. There we go. Okay, so this next one is NFS version 4.1 improvements. Out of curiosity, are many of you using NFS? Okay, quite a few. And version 4.1, anyone up there yet? So most of you, I guess, are still using version 3. So just to tell you about what we've done with the NFS 4.1 in vSphere 6.5, I suppose primarily we have the VAI NAS offload primitives now supported on NFS version 4.1. So up until the vSphere 6.5 release, we only supported this with NFS version 3. And so we've had requests from a lot of customers that they want to be able to offload certain tasks to the array. Just like we talked with the block storage, but be able to do that on file storage as well, or NAS storage. And so we can do that now with the vSphere 6.5 release. Of course, your storage partner, your NAS storage array partner needs to be able to provide you with that plugin. It's different to block storage. Block storage, we have it built in, but we need a plugin from your NAS storage array vendor in order to consume these primitives. And so, yeah, what we've had in NFS version 3, we now have in 4.1. And just some enhancements around Kerberos support as well. NFS 4.1, we've IPv6 support now as well. And also AES encryption is available in 6.5 for those of you who are interested in NFS 4.1. iSCSI improvements then, what do we do? Well, primarily it was all about port binding. Port binding is a way that we can do multipathing with the software iSCSI initiator, so we can associate the initiator with certain VM kernel uplinks. The problem with this is that as soon as you did that, you lost the ability to route the traffic. So the number of service requests that came into our GSS saying, I've just implemented multipathing through port binding, and now my initiator can no longer see the target. And the problem with it is that port binding never supported the routing of the iSCSI traffic. vSphere 6.5, now fully supported. So you can implement port binding and you can route your iSCSI traffic between your initiator and your target.
Just because you can doesn't mean you should, though.
Good point. But a lot of customers do. Yeah. So the second part of that then is just a UEFI iSCSI boot. So this is the ability to boot from an iSCSI LUN using the new UEFI mechanism. So, and then I think we're going to close with you. We're going to talk about NVMe.
So yeah, the last topic here quickly talk about is NVMe. I mean, you probably go to the show floor, and probably 80% of the storage vendors are going to hit you over a bat that says NVMe. So we certainly want to talk a little bit about it here. And so this is kind of VMware's beginning of their NVMe journey, what they're doing for the full NVMe stack support, and of course having a virtual NVMe adapter for your virtual machine. Right? Today you're using the SCSI ones, right? Paravirtual SCSI adapter, LSI logic, et cetera, et cetera. So in 6.5 they introduced the virtual NVMe adapter. Right? This allows for, if you have internal NVMe drives, right, in your ESX server, you can better access and leverage the concurrency offered by the NVMe protocol. Right? There's a far more concurrency that it offers, right, than standard SAS connections with some of the bottlenecks inside of SCSI itself. And so you can get some noticeable performance benefits when you have NVMe internally to that host. Now, if you have an NVMe array, but there's still kind of the SCSI connection, NVMe inside the virtual SCSI stack, ESX is going to convert it back to SCSI, and so you're probably not going to get much performance benefit for like SAN-based storage or something like that with that today, because there's still some stuff inside of these internal stack, the SAN, so forth, that might need to be changed to really take advantage of the performance offered by full NVMe. Right? So if you're using Paravirtual today and you with SAN storage and upgrading this, you're probably not going to see a huge difference. But if you have NVMe drives inside your host, you can definitely see a difference, right? So this is probably important to look at from that. As far as concurrency configurations, right, there are some improvements around here. How many outstanding IOs you can have per virtual disk is the same as Paravirtual, but overall you can have a lot more in-flight IOs to that virtual SCSI, virtual NVMe adapter than you can with Paravirtual. Right? So there are some performance benefits there if you have the internal NVMe, right, around this. Kind of one thing to note here, this one bullet, it supports kind of the basic spec for NVMe. So things like in-guest UNMAP, not going to work with this today. Right? NVMe spec for basically its version of UNMAP is called deallocate, and it's in a special segment of the NVMe spec that's not currently supported. So there is certain use cases where this is beneficial, certain ones not. But I definitely keep an eye on VMware and your storage vendor and NVMe, because this is not stopping, right? This is where everything's moving towards. So this is a really important first step around it. All right. on that
So
note?
we get beat over the head about surveys. So please fill out the surveys. And I think we have a few minutes.
We have some time for
Q&A.
questions, of course, afterwards too.
And I think there's a microphone, so if you could just speak the question into the microphone.
Otherwise, thank you.
Yeah.